The second derivative and concavity. Let y be some function of x. If the second derivative at the point where x equals a is less than 0, the curve is concave down at x equals a. If the second derivative at the point where x equals a is greater than 0, the curve is concave up at the point where x equals a. And if the second derivative at the point where x equals a equals 0, there is a possible point of inflection, which is a change in concavity at the point where x equals a. And further testing is required to show that the point found is in fact a point of inflection. Now the second derivative represents the rate of change of the gradient of the tangent to a curve from left to right. And here are three examples. So the first example shows a concave down section of a curve. And this is where the second derivative is less than 0 in the interval. And we can see that the gradient of the tangent from left to right is getting smaller. In this diagram, this shows a concave up section of the graph or section of the curve. And we can see here that the gradient of the tangent is in fact increasing from left to right. So the second derivative is greater than 0 in this interval. And lastly, this curve here shows a change in concavity at this point here. And this is where the second derivative is equal to 0. But the second derivative to the left of the point of inflection is negative, and the second derivative to the right of the point of inflection is in fact positive. So this point here is in fact a point of inflection, and it indicates a change in concavity at this point of the curve. The following is an example on finding points of inflection. Find any points of inflection on the curve y equals x cubed plus x squared plus x plus 1. The first step is to find the first derivative. F dash of x is equal to 3x squared plus 2x plus 1. The next step is to find the second derivative by differentiating the first derivative. So f double dash of x is equal to 6x plus 2. Next, we solve the equation f double dash of x equals 0 and f double dash of x is equal to 6x plus 2. So we're going to solve 6x plus 2 equals 0. And solving for x, we get x equals negative 1 over 3. Hence, there is a possible point of inflection at x equals negative 1 over 3. Next, we test the possible point of inflection, and we can use a table to do that. There are three columns in the table, apart from the column that has x and f double dash of x in it. So three columns that contain values. The middle column contains negative 1 over 3 for x, and we know that the second derivative is 0, so that's the first column I'll fill in. Next, I choose values of x around the point where x equals negative 1 over 3, and two convenient values are negative 1 and 0. And then we find the value of the second derivative where x equals negative 1 and 0. So when x equals negative 1, the value of the second derivative at that point is equal to negative 4, which means the curve is concave down at the point where x equals negative 1. And when x equals 0, the value of the second derivative is positive 2, which means the curve is concave up at the point where x equals 0. There is a sign change in the second derivative around x equals negative 1 over 3. So what we're looking for is a sign change around x equals negative 1 over 3. So whether it's negative to positive or positive to negative, as long as there is a sign change, that means that the point that we're interested in is in fact a point of inflection. Hence, a point of inflection exists at x equals negative 1 over 3. And finally, to find the y coordinate of the point of inflection, we substitute x equals negative 1 over 3 into the original function. So x cubed plus x squared plus x plus 1. So f of negative 1 over 3 is equal to 20 over 27. So therefore, the coordinates of the point of inflection is negative 1 over 3, 20 over 27.